Welcome to Maths with EJD. Today, or rather in this video, I'm talking about trigonometric versus hyperbolic functions. In one or two previous videos, I probably have established the similarities and differences between trigonometric and hyperbolic functions, and the fact that they look alike in certain areas, or they have some things, a bit of similarity. So let's go and talk about that today. First of all, can we consider um relationships? Relationships. Okay. Relationships between trigonometric and hyperbolic functions. Okay. So it's important to see that trigonometric functions such as sine, cosine, and tangent. Of course, there are other three. So, but let's stay with this. And hyperbolic functions, such as sine, cos, and tan, share many mathematical properties, and forms. Yet they also have distinct differences in their nature and applications. Okay, so having established that, let's talk about analogies between trigonometric and hyperbolic functions. So, first of all, let's consider them in terms of exponential definitions. They both can have exponential definitions. For instance, both types can be defined using exponential functions. So, for instance, we talk about trigonometric functions, trigonometric functions. So here you have sine x. Sine x can be defined as e raised to power ix minus e raised to power minus ix divided by 2I. That's so that's like some complex stuff. And then you can have cos x defined as e raised to power ix plus e raised to power minus ix divided by 2, just 2 now. So 2I for sine, 2 for cos. Then if we talk about hyperbolic function, so when the function is hyperbolic, you have something similar, but now it's sine x, we know the definition that here we have sin x is equal to e raised to power x minus e raised to power minus x divided by 2, while cos x is equal to e raised to power x plus e raised to power minus x divided by 2. The only difference here is the sign. Okay, then that's about trigonometry, talking about them in terms of exponential definitions. So if we go ahead and consider differential equations, that's the second thing. Two, differential equations. Differential equations. So it's important to know that both trigonometric and hyperbolic functions satisfy similar differential equations. So, for instance, trigonometric functions, right? For trigonometric functions, you have that d squared, dx squared, that is the second derivative of sine x, is the same thing as minus sine x. So if you want to, replace this as some kind of differential equation, it's more like saying that you have d squared y dx squared equals minus y, So you can have d squared y dx squared plus y equals 0. So you can look at it that way. Then, of course, for hyperbolic functions, you have something a bit close to that. So for hyperbolic functions now, imagine when you have the second derivative, d squared x squared of sin x. Then when you differentiate sin x, you get cos x. When you differentiate cos x, you get sin x back. So you have sin x as the second derivative of sin x. So that implies that you have something like d squared y dx squared equals y. So that means you have d squared y dx squared minus y equals 0. So not exactly the same, but something really close. So you go back to sine and sin when you differentiate the second time. Okay. So next we have something about, I think we've talked about this a couple of times. That's about the Pythagorean. They have Pythagorean-like identities. Pythagorean-like identities. Okay. So for trigonometric functions, for instance, you have sine squared x plus cos squared x is equal to 1. So this is a very important identity that is useful for so many things. Then we have in the hyperbolic context, we've also seen this a couple of times in previous videos. So this is actually cos squared x minus sine squared x is equal to 1, like this. So that is for the hyperbolic. So they look Pythagorean-like in nature. And then we can talk about the fourth one. So if you take the fourth one, which is addition formulas, they tend to have something similar in this regard. So for addition formulas, so for trigonometric, so the addition formula in the trigonometric context is sine x plus y equals sine x cos y plus cos x sine y, and so on. Then, of course, you can talk about sine x minus 1 and all that. So it all follows. Then you have hyperbolic. For the hyperbolic type now, for the hyperbolic function, So here you have sin x plus y. It's just about the same. That's sin x cos y plus cos x sin y, like that. So that's about addition formulas. So that takes us to some differences between them. So let's talk about differences between trigonometric and hyperbolic functions. So we've seen some similarities already. So talking about the differences, we can talk about their nature and behavior. Nature and behavior. First thing, nature and behavior. So it's important to see that trigonometric functions are periodic. They are periodic with a period of a revolution, that's 2 pi, and are bounded. They are bounded. They are bounded between the closed interval -1 and 1. So just like when you see the sine and cosine graphs now, they are always between -1 and 1, and they reoccur. I mean, they have a period of 2 pi. You know, after every 360 degrees, you get the same result again. So that's for trigonometric functions. Now, on the other hand, hyperbolic functions are not periodic. They are not periodic. For instance, you see that sin x is unbounded. Sin x is unbounded. Okay. So because you know sin x, if you remember, it's something like this. Like you're going here and you're busting out that way. That is sin x. So sin x is unbounded. And cos x is always greater than or equal to 1. It's always greater than or equal to 1 because the curve is something like this. So if this is the origin, so look at 1 here. So cos x is always like, it's the minimum point of cos x is 1. So cos x actually lies between 1 and um it's always greater than or equal to 1. That, I think that's just the simple thing to say. Okay, so that's one thing in talking about their nature and behavior. Then the next thing is their geometric interpretation. Two, so don't forget, this is cos x now, you know. So sin x is something like this. It busts out here. It's better still. It enters here, and then emerges out of this place. And that is for sin x. So sin x is unbounded. While sin x is unbounded, cos x is always greater than or equal to 1. So the least value of cos is 1, like we said already. So let's talk about their geometric interpretation. Geometric interpretation. Geometric interpretation. Okay. So first of all, trigonometric functions relate to secular geometry. So trigonometric functions have business with circle, the unit circle. Okay. While hyperbolic functions relate to hyperbolic geometry. So that is, they relate to the unit hyperbola. relate to the unit hyperbola. All right. Then we have the third point, which is about their derivatives. So if we talk about their derivatives, for instance, we see that d dx sine x is equal to cos x. Okay, that's one thing. On the other hand, so this is for trigonometric now. So this is trigonometric functions now. Then this is hyperbolic. Okay, so d dx of sine x is cos x, whereas d dx of sine x is cos x, like that. So see where the difference now lies. By the time you now differentiate cos x, d dx of cos x is equal to minus sine x, whereas d dx of cos x is still the same sine x, like that. So that's one difference. So you see that while the sign changes here, it does not change here, like that. So that's a kind of difference. Now, having said all of these things, talking about the similarities and differences, can we discuss them in terms of Euler's formulas? So let's discuss them in terms of Euler's formulas. Uh, Euler was that mathematician that had a whole lot of contribution back in the days. So Euler's formulas. So how do trigonometric and hyperbolic functions relate when we talk about Euler's formulas? Let me write that properly for clarity. Euler, that's Euler, Euler's formulas. I remember I used to call that Euler's. But I mean, I think the Germans, it's supposed to, it's a German name. So the Germans would rather call it Euler or something like that. So Euler's formulas. So talking about trigonometric functions, first of all, okay, I think I've adopted this style of, having this header in a different color. So talking about trigonometric functions, trigonometric, trigonometric functions. Okay, we have that e raised to power ix is equal to cos x plus I sine x. And of course, e raised to power minus ix is equal to cos x minus I sine x. That goes. And then we can also talk about hyperbolic functions. So for hyperbolic functions, how does that pan out? Hyperbolic functions. Okay. So this is like, so for hyperbolic functions, we have e raised to power x equals cos x plus sine x. So, and of course, you can easily try this out. If you add cos x plus sine x, it gives you e raised to power x here. And then this is e raised to power x. On the other hand, if you have e raised to power minus x, it's cos x minus sine x, like that. You can also just add those together and you see that that's what it gives you. So you can see that these formulas connect exponential functions to both trigonometric and hyperbolic functions, revealing their underlying structures in complex and real analysis. Interestingly, that's what we're going to see in the next video. But before we finish up with this video, let's look at some applications, some applications in both domains. So let's revisit some applications and see probably new ones. So applications of trigonometric. I don't know if I can call that joint, if that's allowed here. Joint applications of trigonometric and hyperbolic functions. So now we have First of all, calculus and differential equations. Calculus and differential equations. So how does this come in? So we know that hyperbolic, and trigonometric functions are used to solve differential equations. For instance, the differential equation d squared y dx squared. I mean, we just saw this not quite long. D squared y dx squared, which is equal to 0, has the general solution, a cos x plus b sin x. That is y of x now. When you solve a differential equation, you get a function. So here you're solving to get y. So y of x is a cos x plus b sin x. So that is that. Then trigonometric functions, you can say that trigonometric functions solve wave equations. They solve wave equations and describe, of course, wave equations are also differential equations, and they describe periodic phenomena. Okay, so having said that, we can move on to the second thing, that's complex analysis, which I'm going to elaborate a bit more in the next video. So let's talk about complex analysis and Fourier series. Complex analysis and Fourier series. So here, Euler's formula, like we saw before, Euler's formula, which is e raised to power ix equals cos x plus I sine x, is fundamental in complex analysis. Used in computing complex integrals. And transforming functions via Fourier series. So, for instance, a periodic function f of x can be represented as f of x equals a naught plus summation from n equals 1 to infinity of an cos nx plus bn sine nx, like that, so that we can now move on to the next thing, talking about hyperbolic geometry and relativity. There's a third application, hyperbolic geometry and relativity. So here, hyperbolic functions appear in hyperbolic geometry and special relativity. And then the Lorentz transformation, which relates time and space coordinates in different inertial frames, uses cos theta, or rather cos phi, and sin phi, where phi is equal to inverse tanh, that's arctanh V over C, such that T prime is equal to T. Let me write that more clearly, such that T prime is equal to T cos phi minus X sin. Now we're talking about time and space. So T for time, X for space. So X sin phi, and then we have X prime to be equal to minus T sin phi plus X cos phi. So you see time and space connected together. So the derivative of time is this, while the derivative of space is also X prime. So derivative of time is T prime, and that is T cos phi minus X sin phi. And then the derivative of space is minus T sin phi plus X cos phi. So this system, represents the connection between time and space. Okay. Now, we can also have an application of all this in electrical engineering. We have application of this in electrical engineering. Have I been numbering before? Yeah. Electrical engineering. So here, hyperbolic functions describe the behavior of electrical transmission lines. Where voltage and current are modeled using cos X and sin X. Of course, we can talk about the idea of catenary too, right? Like a cable hanging on a pole, something like this. You have a pole here. Of course, maybe I guess it's not the actual the application we're talking about in this case. So, but when you have a pole hanging this way, so it's actually called a catenary, which is modeled using hyperbolic functions. Catenary. So, of course, we can also talk about the behavior of electric transmission lines, talking about voltage and current in the context of sine and cos. Okay, so we have that application in electrical engineering. So lastly, we talk about uh signal processing. Number 5. You have signal processing. So for signal processing, now we talk about trigonometric functions. Trigonometric functions are extensively used in signal processing for Fourier analysis. Breaking down complex signals into simpler components. So, and that's why it's possible to have, you can break down sound and things like that into smaller bits using this kind of expression. So with this, we come to the end of this particular video. If you've followed up to this point, thank you so much for always being here. And if you have not subscribed, be sure to do that. Hit the subscribe and hit the notification bell also, so you can always get alerted when a new video is released. And don't forget to comment, like, and share. See you next time. Bye.